So welcome everyone to another CAP seminar. Today we're very fortunate to have two grad students and who are actually two CAP fellows that are going to talk about the research today. So the first one is going to be Melanie Archipley, and Mel is going to talk about the point source catalog, preliminary again, point source catalog from the first 3 years of the South Pole Telescope.
Thanks. I'm really excited to be here and actually see everybody in person because I've been attending these virtually for a really long time. So I'm really excited that their experience is so full. A lot of you have seen me talk about this over the years. This is what I've been working on for years. And I am really stoked today to actually show you like the catalog. It's 3 years of data, but it's the catalog. So that's really exciting. And thank you so much for coming. Okay.
Did you plug in the dongle thing?
Yeah, I did, but it's not even letting. Oh,
Yeah.
there we go. Okay. So the SPT survey is the data that I'm working with. This is the field that is being currently observed by the South Pole Telescope. It's called the SPT-3G field. So this entire time, I'm going to be talking about 3G, which is the data that I'm working with, and then SC, which was the first iteration of these SPT surveys. So anytime there's like SPT-SC or SC anywhere in here, that was the first catalog. So that was like a huge thesis. And the final version of that catalog came out in 2020, and I have now started working on the next generation of data. So what I want you to think about or like keep in mind is just how much deeper this current data set is than SC. So we've got like an order of magnitude increased depth at 90 gigahertz and really improved depths at the other ones as well. So that is partly why this catalog has so many more sources in it than the first one, even with a smaller observing field. So this is 1,500 square degrees that I'm working with. And these are the current depths, and after the entire survey is done, which will be in another couple of years, so yeah, until 2023, we'll get even deeper. So I just want to situate that. So if you've seen me speak before, you know I've been presenting this, like working on this catalog for a long time. So if you saw this in April, there's a lot of similar looking plots. But what I want to tell you that I have today is there's 9,000 more sources that I'm showing today than there were in April. So how did that happen? Like it's the same data. I have an additional year of data, improved the methods a little bit to tighten everything up and increase the ability to detect these sources, and also expanded the useful area for source finding. So I was able to kind of go out farther on the edges to get more sources. So also to contextualize this, the SPT-SC catalog was less than 5,000 sources. So to squeeze out another 9,000 in a couple of months to show you, I'm like super stoked about the entire catalog that I'm showing today is over 22,000 sources. So that's great. So also just to tell you how what we're actually seeing, we're mostly seeing two types of physical mechanisms or two types of emission. One is synchrotron radiation from AGN, and one is thermal dust emission from reprocessed UV starlight in dusty star-forming galaxies. So lots of star formation, dust is reprocessing light into the millimeter and submillimeter, and that's what we're primarily seeing these two populations. So I'm going to come back to this many times about how we determine what type of emission we're seeing, but this is kind of the just put it in your heads. This is physically what we're observing. So how does the source get into the catalog? I'm not going to bore you today with clean algorithm or optimal filter or anything like that, but I do want to say how this is constructed. So basically, I count a source if it is detected at least 5 sigma in any of the 3 bands. So if it's, yeah, it can be 90, 150, or 220. If there's a detection at 5 sigma, it makes it into the catalog. If it's detected in multiple bands, I basically do like a radial association to say this is the same source. So if it comes up and there's in 90, and then in 150, there's a similar, like there's a detection at a very close location to that. Then I say, that's probably the same source, call that the same source and pull the flux that way. If it's detected in just one band, like at 5 sigma, but not at the other two, I basically go to the other two maps and pull the flux from that pixel and report that in the catalog. So the catalog goes, so that's why this the final one has like so many more sources, is for all those detections that were not necessarily 5 sigma at each band. So each of the GIF, like the 90, 150, 220 there, is just the 5 sigma detections in each band. Yeah.
So at 5 sigma, what's the probability of one to be fake?
I haven't got that far yet. That is in progress. Yeah.
What's that separation that you consider to be close?
Less than an arc minute. I think it's like 0.66 or like 2/3 an arc minute, something like that. Yeah, and that is right now kind of like guesstimated, but will eventually be well motivated by the source density that we're dealing with. And yeah.
Maybe are the sources like galaxies or what?
They're galaxies and they're AGN, like which are blazars, and they're stars as well. And who knows what else? Yeah.
Probably I missed it, and probably I missed it on all the talks before, but could you remind the pixel size and is the size just for reference?
Yeah. So the beam is about 1 arc minute in all the bands, and the pixel size I'm using is a 1/4 arc minute. Yeah, good questions. Fair.
Right. So if you put a 1.5 arc minute separation, would the beam actually affect the sources?
Sorry, it's less than an arc minute to associate. Yeah, and then the beam is over an arc minute in each of the bands.
Yeah.
Does that? Yeah. Okay. So when I first have the catalog, all I have is where it is, R index, the signal to noise in each of the bands, and the raw flux in each of the bands. So I have to go through, this is kind of the part that I'm working on now, all these steps. I correct the raw fluxes for different biases. That's called deboosting. I'll talk very briefly about that. And then I cross-match all these to external catalogs. So is this source in all of these other catalogs that we're looking in different wavelengths than millimeter? And then I look at the spectral behavior of the sources by comparing the ratio of the fluxes at 90, 150, and 220, and then try and answer the question like what is weird, what stands out, what might be worth following up. Really quick on deboosting. So all this is because there are more dim sources than there are bright sources in the universe. We would detect more dim sources writing positive noise fluctuations than like dimmer sources writing negative noise fluctuations that make it over the threshold. So there's an artificial bias in the catalog that is affecting sources near the detection limit. So that's like, this is the detection limit in each of these. So all I'm showing here is just what the raw flux that I detected was and the deboosted flux, just showing that for a lot of these, they have to get like bumped down. This is like imperfect in some ways when I'm dealing with negative fluxes or weird things happening, but and this is also something that is very, very work in progress because we're adjusting the assumptions made that go into this. But just want to mention that we are correcting for this bias that's affecting these like very dim sources. When we cross match, so what we're trying to answer the question is kind of what emission are these sources showing up in other catalogs, and what does that tell us about what they are? So if the source is matched in ASCAP, for example, which is a radio catalog, then it has radio emission, might be a blazar. Same with Fermi, which is X-ray. So those are going to be those really bright blazars. And then if we're matching to IRS and Ys, those are low redshift close by galaxies. So those are going to be the dusty sources. And everything that's left over is kind of the like place to go looking, because that means it's high redshift and dusty. So hopefully going to be star forming, interesting, strongly gravitationally lensed stuff that we're going to follow up. And that's what was done with the SC catalog. And now we have all the wonderful follow up like with JWST and ALMA. So just to show some of the flux ratios. So this is every source in the catalog, 22,607 sources, 150 flux, 220 Y, and all of their associations. So black is no counterpart. So you'll notice things like the no counterpart sources are very dim, they're much dimmer. Those Fermi sources are very bright, those are the brightest blazars. So this is kind of a quick way to look and see where these populations are falling. You can also very quickly see the dusty sources that are matched in IRAS and WISE are all the blue ones on this alpha line. So I'll talk about alpha in just a minute, but alpha is the spectral index of those sources. And same with the, so as I mean, SPT-3G has both populations because it's also a millimeter survey. And then you see the radio association with WISE, or sorry, with ASCAP, all the red stuff along the spectral index pointing to synchrotron emission. Yeah.
So it would appear that the red, purple, and orange points are above the black points for no counterpart. So we're mostly seeing them on the bottom left. Is that real? Like that trend that they're mostly in the bottom left, or are they just under all the other points?
They're under. I mean, so yeah, I didn't exactly plot just the black ones somewhere. But for the most part, the black no counterpart sources don't go like that high because they have been found elsewhere because they're bright enough to be found elsewhere. So those will have associations. So mostly the unassociated ones are dimmer. Yeah. So about that spectral index and what we're doing with it, that is just a ratio of fluxes. It's trying to relate each of the fluxes to each other and tell us the spectral behavior of the source. Is it synchrotron, dusty? I mean, that's a shorter way of saying, is the spectrum falling, rising? And then there's some other weird spectral behaviors that I'm working on looking into. But so what I wanted to say about this was that in SPT-3G, we were seeing over 80% of the sources were synchrotron sources, and about 20% were dusty. And now in this 3G catalog, we're almost at half and half. And this has to do with the fact that because we're at these lower, at this increased depth or lower depth, the source populations completely changes. And this is really fascinating because it means that those sources are kind of evening out number-wise. We're going to see the same numbers of lensed and unlensed SMGs, and way more dusty sources than we were seeing before, which is cool. So that's what I wanted to mention about that. If we plot that spectral index for both 90, 150, and then 150, 220, we can see all of the sources sort of fall into these quadrants of what their spectral index is doing or what the flux is doing. So I just kind of wanted to take you through an example of a source, this pink triangle. So here's a random source that has each of these fluxes. We can get its alpha by just comparing alpha actually takes into account the frequency that you're looking at, but you can just look at the flux and say, okay, we're falling or basically flat between 90 and 150. We're falling between 150 and 220. If you plot that here, we see we're having falling type of spectrum, which is where all of those blazars are going to be. And then also when we add in the associations, we know it's cross-matched in ASCAP, it's cross-matched in Fermi, it's got radio X-ray associations, it's going to be a blazar. The photons that we're seeing in millimeter is from synchrotron emission. So that's kind of how this goes for 22,607 sources, is figuring out where they go on this plot. Yeah.
Motivation for the dash line, like the crosshair, I guess, at 1.5 on Y and 0.5.
Okay, so yeah, I didn't include the plot that exactly shows that the Y is 1.5, but that's where in SC where the population sort of fell over. So all the synchrotron ones were at that, and then the dusty ones were there. So it's just kind of to visually help you, I guess, put it into these dipping, rising, falling, peaking quadrants. So just kind of a plot, but yeah.
Well,
okay.
So the top left quadrant, what are these dipping circles that have possible warnings?
Yeah, don't know yet. So that is something that we're gonna try and figure out. Is this physical? Is what's happening here? So both peaking and dipping are quadrants that are going to be investigated very thoroughly, hopefully. But yeah.
So when you cross-measure with the external, how do you deal with the source confusion? Because like you mentioned, you have a very large peak size, and there might be multiple sources.
Yes, exactly. So we do have to take into account the source density of all these other catalogs. And so that's a good point. I should say that each of these associations is not the same, like 2/3 of an arc minute association. So for ASCAP, I think we use like 1/3 of an arc minute, and for one of the other ones we use like an arc minute and a half or something, exactly to deal with the different mean sizes of us, the other catalogs, and the source densities in the catalogs. So yeah, I'm taking that into account.
So I'd imagine a bunch of your sources, particularly the black points that are fairly dim, would have very uncertain spectral index. So are they cleaned out here? Do you have some requirement on detection in multiple bands? Do you get a good spectral index, or are they sort of peppering that lower right corner is just like, these are the ones that are probably fake because we don't know what they are?
Yeah,
not fake. We just don't know what
we don't know what they are. So right now, in this in literally the spotlight I'm showing you today, totally, like, haven't investigated this thoroughly enough to say that this is completely pure and that all of these are real. And that is getting, so basically once I do the purity and kind of completeness calculations more robustly, I'll be able to say, like, and for the peaking ones, like either of these are like weird uncertain spectral indices, or they're super cool,
Sure.
Who knows what this object is doing in space, kind of objects. So yeah, that is currently ongoing.
Is there a reason why you don't see any of the black lines in the detection?
Sorry, would the black points? There are some in here.
Well, there are some, but I mean, there are lots of black points.
Oh, yeah.
Compared to the big one. I mean, if they're really uncertain, usually you have like equal number of black points.
Maybe they're not that uncertain.
The green point in the different case, that must be some like right Fermi source.
Yeah. Yeah. Well, I mean, so I mean, this brings me perfectly to the next slide, which is like, what do we do with this? Like, and how do we find the weird ones or the interesting ones? Exactly this is looking at that plot going, why is that Fermi source there? Why is there so many no match counterparts in this one but not this one? And so it's exactly that's happening next. And we want to be able to extract the sources that are going to give us the most information that we can glean about galaxy structure, formation, evolution. And we are especially interested in galaxies or objects that are high redshift, that have uncommon or weird emission patterns, like if they are actually peaking or actually dipping. Also these strongly lensed objects, because we get magnification for free, which is great. And then who knows what else we'll find. So that is what I started doing a little bit. So here's again that 150, 220 raw, oh, spoiler, plot. And there's like some sources that are kind of strange. So what's happening there? Actually, so these black points are all of the sources detected at greater than 5 sigma in all bands that have no counterparts. That's 78 sources. So I feel like that's a good starting point to say, like, these are high significance. No one else has seen them. What's up with them? So starting there, looking at this and seeing that these fall into that category, like, what is that? So one of them is it's an object we've seen before with SPT-3G. It's a cluster lensed submillimeter galaxy, meaning that a dusty submillimeter star-forming galaxy is being lensed by a galaxy cluster. And we see that in, so this is 90, just like a thumbnail, 150 and 220. So we see the decrement very clear at 90. The decrement starts to kind of go away 150, but you can still kind of see it. And then at 220, it's emissive. So this is a friendly source that we've seen before. And there have been papers written about it, and that's super cool. And here's one that has not been in any other catalog or followed up that I found that appears to maybe also be a cluster lens submillimeter galaxy, where this 220 detection is at 8.5 sigma. So this is not, it's not so dim. And here is the decrement, like, huge in 90 and 150. So this is the beginning of treasure hunting and seeing where we're going to go with this. Yeah.
Is that a known SPT cluster?
I didn't look actually. I guess I kind of assumed it was so massive that like it's gotta be.
It must be given that.
I mean, yeah. So
What's the position accuracy with which you know these sources? Because the scale on your deck is like several degrees for the looks of it. How large is this on the sky? Because you can probably look for this in DES.
Can you start hearing the question?
So it looks like your declaration scale, at least from my understanding, is pretty large. What's the positional accuracy for which you know these sources? How compact is that? What's the uncertainty region? And can you like just search in DES at that array, like
I don't know yet. I'm not sure. Yeah, I don't know yet.
Well, the beams in arc minute, the solenoid is 8.5, so you know the position to 10 arc seconds. Yes, you can look in DES, but the dusty source will be invisible by definition. But anything like that will be booming as a cluster. So you'll see a massive cluster. The source of the 220 gigahertz will be completely invisible without ALMA.
I mean, it could be.
Still wouldn't be visible.
Could be what kind of you say?
It could be a cluster member, he's saying. Our selection function is not that great for a redshift 0.5 object. It's actually for the same luminosity, more sensitive to something redshift 4. Also, if it was in a cluster, it'd be moving in IS.
And there's no counterpart.
So the reason why it's not a cluster member is actually because it's way behind the lens. That's and you get that from the flock, from the brightness.
Yes.
We agree. These are probably like in the catalog, in the SC catalog.
The
that
cluster. Well,
Yeah.
yeah, I'm sure this cluster is in SPT. But this wasn't. This was not an SPT. So.
Maybe if you check the SC flux between 90 and 150, I think if the source is in there for sure, then 150 flux will actually be different.
Well, I also cross-matched this with SC, and so this is an SC. I don't actually know if this is just not in the same area or if I just didn't see it.
I think he's implying that source is filling in some of the decrement, like on the previous source.
Yeah.
See how it's filling in a decrement. So I think he's saying you could use that as a comparison.
Yeah. Well, I love this because a whole room full of people can find about all of these 20,607 sources to see if they're interesting and worth more studying. So I guess just to get into the end here to make us feel good, the source counts that I have so far for this 3-year SPT-3G catalog do track perfectly with the SC catalog. So SC is the red points and blue is 3G, so we're getting much deeper, which is great. And here we are basically. So this is 220 flux, and the number of sources greater than some flux in per square degree. This pink point is the 3-year SPT-3G catalog. This region where we are at depth is, as I said before, is fascinating because each of these source populations is going to be the same. So what are we going to do to deal with unlensed SMGs, like looking the same as lensed SMGs? And also we're going to have the same amount of synchrotron sources and so on. We're already seeing that with the ratios that I'm getting, about half and half for synchrotron and dusty sources. So this is where we're at, and we have lots more to do, and I'm really excited. And Kedar told me to say this. So I said it was cruel to put me with the JWST data in the same seminar, and he said, well, if you don't do what you do, then we can't do JWST. So that's the end of the catalog for now.
I have time for a few questions.
Yeah, so instead of looking at the entire quad, have you looked at quads of weeks and then you fix, for example, you pick like some bright source or Linux radiation?
Sorry, look at quads of what?
Quads have like a few weeks of data rather than
Yeah.
and then look for radiation spectrum.
I have not thought about doing that.
But one could use the thumbnail server to do that trivia.
Yeah, that would be interesting. I have really haven't looked at like individual seasons or shortened the amount of time that I've looked at the data. Just looked at the 3-year POAD basically, but that's an interesting idea. Yeah.
Because the 78 sources that you mentioned that you're not out, they're actually variable. And that's the chance that you want to find another. Yeah, that's true. I mean, everything that I'm doing and I've said really doesn't address like sources that are popping in and out of the detection range completely, which is an entire other avenue that we should maybe go down. But yeah, definitely.
Wise catalog is quite large, so I get that in 10 or second you to find a few sources. Yes.
Yes.
Likely galactic have you sample
Yeah, so I just kind of skipped past it, but it was written on the slide. We do make a flux cut in band 4, what I think is band 4 Ys. Do they have to be at least, or maybe it's they have to be below.
That's right. Is it, they have to be greater than, yeah.
Yes, yes. Oh, yeah, sorry.
I missed it. Thank you.
Yeah, yeah. That's to exactly deal with, or try to deal with that a little bit.
No, I'll ask one question. So when is the paper coming out?
I mean, well, every time I think I've done the hard part, like another hard part kind of comes up. So, yeah, I'm hoping sometime in the next year, spring, summer 2023. I'm going to pull this December. Just got my PQ. I didn't tell you yet, but I just got my yesterday. I got my PQ, so I'll have lots of no internet time to sit and yeah, yeah, that's written up.
That's good.
Yeah.
All right, if we have no more questions, we'll take Mel and then.
Yeah.
Thank you for keeping.
So
Yeah.
I'm amazed. I'm so
No, well done. Well, you spoke great fun.
because I was
I
like,
did the
oh,
same.
I'm gonna run out of time.
No.
But- Oh. Should I get on? Oh,
Yeah.
oh.
Can everybody hear me, right?
That look okay? Give us a sign.
It's okay. It's okay.
Okay. Well, gosh.
Yeah, are you on Zoom? Can you see if it looks okay?
Beautiful.
Perfect.
Okay.
Okay.
See if this works.
Perfect. Okay, so with perfect timing, we're ready for the second presentation today, and we'll have another CAPS graduate fellow, Kedar P. And Kedar is going to actually talk about JWST and the templates from the panchromatic length chart. But that's your templates is the acronym.
Acronym of like targeting, extremely magnifying.
You have a big some of the listed collaborators.
Yes.
All right.
So this is an ERS program. Walking might have already given some spoilers. This is AOT talk. This is a JWST ERS program that we submitted proposal in 2017. That's my first year, spring and summer. And I still remember Joaquin saying the worst thing that could happen to us is you get this proposal. So next half an hour is about the worst thing that happened to us. Last 3 months actually have been the best 3 months that I've been doing research. It's been most fun. I'm happy to share that with everybody and also privileged to do that. So just an overview. I don't know if anybody has been hiding under a rock for the last year. JWST is pretty cool. This is the light gathering power under comparison with HST and Spitzer. So, is that playing automatically?
There's just a little penetration.
Okay, let's see. Fine. So light gathering power for JWST is at least 6 times that of Hubble, and it covers wavelength range corresponding to HST till over here, about 1.6 microns, and also covers the Spitzer. So there's a gap between 2 microns that we have never seen before. And Spitzer was very tiny compared to Hubble and JWST, but that was state of the art at least 20 years back. and all the mid-infrared data that we have, people are still using it. So it's a revolutionary telescope. Everybody knows about it. Main thing to focus on during this talk are the instruments. So I'll be talking about 4 instruments that I've been using. It's mid-infrared instrument, imaging and spectroscopy, IFU, near-infrared camera imaging, and near-infrared spectrograph IFUs. So the wavelength coverage for IFUs and near-infrared camera is like 0.5 to 5 microns. Then you go into the mid-infrared instrument that covers 5 to 30 microns, and that has IFU as well as imaging. So in the collaboration, I'm mostly in charge of reducing mid-infrared instrument data, and I do both imaging and spectroscopy. Just to put out all the field of views for all the instruments. So at any given particular time, JWST will be looking at different patches of the sky, or different instruments will be looking at different patches of the sky. You can use simultaneous imaging. Sometimes some programs have that, but we didn't. NIRCam, you can see there's like 2 modules. There are 2 detectors, A and B, and each one has 4 chips. We basically focus on one of the chips. Since our targets are smaller, we only use 1 module and use all the 4 chips to get our data. So we are doing 6 filters imaging in NIRCam. For MIRI, that's the imager field of view. These 4 small boxes that you see are coronagraphs. This is the main imager field of view, and this is the IFU field of view. So for imaging, we use this particular thing, and we are using 7 filters imaging that. For NIRSpec IFU, it's the first multi-object spectrograph in space. You can see this big chunk over here. That's the multi-object spectrograph. It's a state-of-the-art technology, but we are only using this particular tiny thing, 3 amp second by 3 amp second IFU. So this will give you a cube for a small area. Any questions about this?
Sorry, what does IFU stand for?
Integral field unit. So it's basically taking an image and you are dispersing it to a spectra. So you get spectra as well as image from 3D. A little bit of background of why I'm using JWST. So I'm interested in dusty star-forming galaxies that was found from walking spaces. So previous SPT-3G catalog. And as you can see over here, this is like an updated plot from Model and Dickinson 2014. You can see the dusty star-forming galaxies dominate at lower redshifts till the cosmic moon, and still they have significant contribution at higher redshifts too. You can see the range of LIRs of the objects that contribute to this star formation rate density. So these are these galaxies are forming stars at very rapid rate and are responsible for most of the star formation that's going on here in the universe. So the simulations have been notoriously known to not recover the dusty star-forming galaxies source counts. So that's still a work in progress. And that's why it's important to learn about how dusty star-forming galaxies are formed, what are the physical conditions of these galaxies, what goes on, like what is the duty cycle of star formation, and et cetera, et cetera. So for SPT-3G, we have data from Cassie 2 years back of all our samples. So we have 81 dusty star-forming galaxies, which are lensed and high redshift, median redshift of about 4. And we proposed for JWST using those galaxies. Just for those who don't know gravitational lensing, we have a foreground lens and background source, which is very dusty because of gravity. Light from the background source will get lens, and you'll see a pretty image, something like that in red. You'll see prettier images in the next slides, but this is done for press release when Walking's paper came out, I think. So this is our sample for the templates proposal. So we have 4 galaxies. Walking basically joined hands with the S-gas team. Those are Sloan Giant Arc Survey, and they have cluster lenses, which are lens star-forming galaxies at high redshift, but but their extension is slightly lower. So they are not that dust obscure as our SPT sources. So you can actually see them in HST very, very nicely and highly resolved. So these are HST images. But for us, when we look at HST, we just see the foreground lens and nothing from the background source. Red color over here is from ALMA. That's how we know that our source is lensed. And it's like a perfectly shaped ring. That's one of the famous sources, SPT-041847. And another source that we have is SPT-214750. So same deal over here. Blue is HST that we had before. We don't see anything from the background. So that's why we propose to JWST. For other sources, we did have HST, but we still wanted to get deeper lines or like deeper depths in spectroscopy. So we get other lines and figure out what's going on in them and also imaging.
So Kedar, I have a question for the two Sloan sources. These are, I mean, the sources themselves. That's the lens.
Yeah, no,
that's the lens galaxy.
That's a lens galaxy.
And I'm assuming that then the lensing galaxy is
a bright cluster.
It's okay,
right?
And it's not in the picture.
It's not in the picture.
Okay, because it's much bigger.
It's much bigger. Like this picture basically is for like 3 arc seconds. So if you remember, our IFU field of view is 3 arc seconds by 3 arc seconds. So we chose our target so that our target will fit in that IFU, and that's what's over here. So that's why.
And the objective of the Hubble proposal, or the JWST proposal, is actually to study the galaxy populations with the JWST filters. Is that we wanted to do, rather?
Yes,
the populations of the galaxy that is being lensed.
Yes, so we are studying the background galaxies. So these are all the background galaxies, spectral energy distributions. And the main goal of the proposal is to study the line diagnostics, where the star formation is happening. We can spatially resolve them, get extinction maps, get the morphology of the star forming clumps, and also to spatially resolve SEPs. So this is like the proposal figure. You can see all the imaging figures that we have, 7 and 6. This is mid-infrared, this is near-infrared, and the lines that we are targeting. It's like H alpha, H beta for the S-gas sources and other ionizing lines. And for the SPD sources, we didn't think we'd get H alpha. So that's why we target very shallow H alpha, not shallow, it's still 1 hour on JWST, but also Pash alpha 1 hour and PAR lines. So all these imaging filters that you see are of the order of minutes because we are more focused on IFU spectroscopy. So these particular things that you see, this is like 2-minute depths. And most of this is about 2 to 5 minutes, and same over here. And from near infrared, we are going about 5 to 10 minutes. So these are very cheap observations for imaging. So first data, this was released the same day that everybody else got the data. So this was July 14th, 2 days after President Biden released the first image. I don't know if you can see over here. This is SGAS 1723 MIRI imaging. And you can see some striping over here. That's 1 over F noise that we have to deal with. So this was just the first look, 9 a.m. after the release happened. And this is at 546 microns imaging in MIRI. So for SGAS 1226, the observation window just closed after the commissioning finished for IFU spectroscopy. So we only had imaging, and this is like a 2-minute snapshot. We didn't expect to see anything, but you do actually see some blurred blob over here. So that's kind of sad story. Since we didn't detect and we are spending so much time on it. But it's still detected, and it's not just resolved detection, get an integrated detection. But we also had some other artifacts in the data. So this is like a cosmic ray heading from the side of the detector and leaving a mark. And this continues in other filters. So since this is the first time we are getting data, the Institute also didn't know how to deal with it. So we worked with the help desk, figured out how to remove this, and that didn't take care of it. So you take multiple positions in the sky so that you are dithering, and this is fixed in the detector frame. So this will move, and basically you get a better result and result.
When you say it's shows up in other filters, you do the same cosmic ray persists after reader.
Yeah. So this it left some persistent kind of thing, and it was not getting.
So like a ghosting.
Yeah.
And this is work at the detectors.
Yeah, so it's at the detector level, and these are very short exposures, so you're not like resetting the detectors. Yeah, they're still trying to understand this. So we are helping the institute understand what's going on with their data and like how we improve things in the pipeline. So still for comparison, this is HST, and this is MIRI imaging. The blue is 560 filter, so that's 5.6 microns, and 7.7 microns, and red is 10 microns. So that's the worst quality data you will see today. Moving on to gas 1723. So this is imaging at NIRCam and MIRI. You can see immediately the morphological differences in near infrared and mid infrared. You can see the clump. This is like a mirror image across this line. So this particular clump is image here and here. That's the bright cluster galaxy that Philip was asking about. So you're seeing a red clump pop up at 15 microns, and it keeps getting redder, while other star forming regions are not that red. There is some morphological differences in galaxy. Just to recap, that's HST, MIRI, and NIRCam. There was some astrometric offset in the beginning. We took care of it later. Small details. Yes, I have to play this, but so you'll see shifting from HST to NIRCam and MIRI again, just to pop out the differences in the same regions of the galaxy. Over here. Another one for SDAS 1723 again. This is near spec spectra for SGAS 1723. You'll see something over here. That's the half part of the arc over here. That's the bright red clump that you saw before, and it's getting brighter in Passion Alpha. This is Passion Alpha in the Lens galaxy. So that was about SGAS sources. I'm not that much involved in reducing the data for those sources. Somebody else in the collaboration is doing that. I'm more involved in the SPT side of things. So I'll be talking about that in the next half. So this is the state that we were before JWST for one of our sources. So this is SPT-14750. It's at redshift 2.76. You can see in HSP, you don't see the background source really well. It's mainly the foreground source. And this is big fat PSF of IRAC, where nothing is resolved. So keep in mind this picture, and you can see what's the improvement later. Yeah. So that's this particular source. So the foreground lens and the background source gets resolved very well with JWST. This is NIRCam filters, 4.4 microns, 3.5, and 2.7 microns in RGB. And this is MIRI filters. So that was 214750. This is 041847. You can see the lens getting dimmer and dimmer at higher wavelengths. That's because it's lower redshift source, and it is going below in the SED, and the dust hasn't picked up yet. Or we don't know if there's much dust in the source since it's mostly elliptical. And the background source starts popping up more. So these four clumps are the same clumps in the original image source plane, and they are getting quadruply lensed. Which are the brightest ones. You can also see some features over here that we'll talk about next. Yeah. So this is just to show in grayscale. You're going from 3.5 microns, 4.4 microns, 5.6, 7.7, 10, 12.8, 15, 18, and 21 microns. This is observed frame. You can see the lens getting dimmer and dimmer as you go, and the star forming cloud is the brightest one popping out more and more, getting brighter.
So my question, on that table you showed us earlier, even before you had the JWST imaging on when you had the ALMA superimposed,
yeah,
you had some star formation rate numbers that were fairly high for those two sources.
Yes.
200, the other was 1290. Now that you have the resolved stuff and you're seeing these clumps, are the star formation numbers should get consistent?
Yeah, more or less. Yeah. It's still happening because like there was some near-camp photometric calibration issues, so we are still doing that. But at least in the first one, they are consistent. That is from infrared luminosity and terrestrial optical diffraction. Yes, Brad.
So in the grayscale images you had, why is the foreground getting dimmer in the background being characterized?
Yeah, so this is related to the redshifts of the sources. The foreground is at lower redshift. So there's a star forming clump bump that's about 1 micron in the rest frame. So if you redshift that, say this lens is at 0.2 redshift, so you have to point it at 1.2 for 1 micron, 1.6, and then you get about 3 microns where it starts going down. And for background source, this is at about redshift 4. This is at redshift 4.3. So that bump comes much later, around 10 to 12 microns. Maybe that, what, 10 microns maybe, yeah. So that's where it will peak, and then it will go down slightly and then come back up from the dust. So you have to go back to the SPT plot. So for the foreground source, you're seeing this particular rise. So that's why it's getting brighter. For the background source, for foreground, that will come like this down. Mm. So you're seeing one getting brighter and one getting dimmer. I didn't plot that one there from measure. So once you have that, you can do model the foreground lens position, do a Galfit model and subtract it, and you get these pretty pictures. So this is the same bands, just subtracting the foreground lens, and you can see features popping out more and more. This particular blue clump is at the same redshift as the background source. It's also you may show here. You can see that in the other data as well. So this was not found before. There was a Nature paper for this particular source saying that it's a dynamically cold galaxy, citing E over sigma. And with this and some sort of time thing, we can say it's probably not a dynamically cold galaxy. So half of the Nature papers are usually wrong. And there's this rainbow kind of thing. So there's this particular clump, and there's also another clump that's right over here. We'll get more data about this later. We just have imaging for 1.750. We expect a few data tomorrow actually. So that's more fun. Yes,
that might be a silly question, but at least I know what on a supernova, for example, there's like depending on the lensing orientation, you might have like supernova appear one clump, and then you wait like a month or two, and then like it appears out elsewhere. Can we expect that this is like static, and these clumps that you're seeing are only just a function of the wavelength that you're looking at, and you're not gonna expect that when you observe it again in 2 months you'll find like
if a supernova goes off over there, we probably will observe that again and see the difference. But as of now, I think it's like more of a static. Yeah, it's a galaxy. But yeah, it's something.
Remember why to see it at redshift 4.
Yeah,
1+ is pretty long time.
there's what they do, what Hubble and the rate expansion rate measurements using time delay in quasars for the same source. So I don't know.
Yeah, those are highly variable. This is mostly thermal emission. So there's millions of year time scales.
10 million years.
yeah, that's
If a supernova goes up there, it will. So, any other questions? So slightly taking artistic license and enhancing the previous image by 10 times. You get this. And since we have very high resolution C+ data from ALMA, I'm plotting that in red over here and overlay in NIRCam in green and blue. So you can see it's more or less co-located with the dust, the stuff on optical rest frame optical light and rest frame infrared light, far infrared light is more or less co-located. Yeah. Next, we go on to spectroscopy. So previously, highest redshift known Paschen alpha detection has been at redshift 2.5. That was using Spitzer, long slit, and unresolved. This is the highest redshift Paschen alpha detection known till now. You can see resolved. So that's really cool result. You can see the spectra over here. That's pretty much robust. And Paschen alpha is supposed to be gold standard in star formation rate tracer because it's less extincted than H alpha. So for dusty star forming galaxies, you have to do extinction correction and then match it with IR luminosity to get the star formation rates to match. With Paschen alpha, you don't have to do too much extinction correction as the extinction at 2 microns is much less than 0.6. So that's why this will be very useful. It's just that we didn't have the technology to observe these at higher redshifts. We don't have that much data. But right now with JWST, just going to populate that very much. So this is for SPT-041 again, overlaying Paschen alpha contours on C+, and that's the integrated over the ring. If you take small regions across it, you can see the velocities slightly differing. You can take the average and then compare it to the companion. That's why I say companion is also at the same redshift because we are seeing Paschen alpha from the same region. That's a pretty cool result. Second cool result is the PAR detection. That's also highest redshift. Previous was again from Spitzer, I think, and more from Akari. So for star forming galaxies, we expect to find this hydrocarbon chains. We get excited by them, and we expect high emission in those type of galaxies. If there is an AGN, you annihilate some of them, and the continuum will rise, and the equivalent weight will reduce. So if the equivalent weight can be an indication of AGN presence, but detection versus an indicator of star formation happening there. So we are still struggling with the data a bit. As you can see, there's like 2 different reductions right now. This is the gray ones are the background apertures. So if I plot random apertures in here, here, and here, those are the 3 gray lines that you see. And I'm summing these 2 particular bright clumps in PAR. So this is about 3 noise detection. But you can see right off the pipeline, and after doing some massaging of the data, we are not getting pretty robust detection. So Walking suggested doing some high-pass filtering that gives us this, which looks kind of robust, but we are high-pass filtering the whole data, so it's slightly it's better to avoid that rather than I would rather have this type of thing and then correct some known artifacts rather than doing a high-pass filtering. Yes.
So nice question. So you already knew the redshift of this object, right?
Yes,
so
yeah.
The line, you don't want the line to get the redshift.
Yeah.
You probably want the line to get some equivalent width, and then that equivalent width must be related to the star formation rate.
Yes. Right. And also, if we can, we want to resolve it spatially. So if we can get the same clump, we can get spectra in all, or we can get the lines in all for all the clumps, and that is really cool. We can do like a mapping of star formation rate indicators across the galaxy.
And is your goal, so is usually this is kind of like calibrated, there's like a relationship between the width and the signal to noise, and the star formation rate.
Yeah.
Is there such a thing for how?
Yeah. So from previous Akari data, there's like hyperlux and ULURX, which was taken Akari data and that have a big sample of Star Wars galaxies and AGN or type 2 AGN, and what's the expected equivalent with.
And is your goal, or do you need to transform this kind of like pixelated spectra into like a traditional 1D spectra that you get from, from a slit? Is that what you need to end up? Is that the problem?
That's what we will end up doing, but if possible, we want to do it resolved.
You want to, okay, so you want it in many places so you can actually have.
Yes.
Like
But it looks like in this case, it might not be possible. We might have to do like an integrated one. Yes.
Former chemist question, what is the feature? So pods are a whole class of molecules. What actually is the transition you're looking at here?
I don't know.
Okay.
Nobody knows.
What?
Nobody knows, but it's like, there's carbon rings, and then there's carbon hanging off of it, and it's this. But they don't.
The carbon hanging off an aromatic.
Yeah.
They don't know. These are, for years, these were the 4 unidentified broad features.
Oh, yeah.
Eventually they call them pods in like the 60s, when it was at some point, they were unidentified for years. And then,
And it's just a transition you can't like make in an MR lab.
I mean, people do like, this is like when astrochemistry, where they try to grow silicon carbon grains and then measure it. But
Interesting. Okay. Thanks.
This is the weakest one of all the other parts. There's 6.2, 7.7, and 11.2 microns. Those are much brighter than 3.3. But with the redshift that we have, 4.2, we can't reach that.
they used to be called UIVs, unidentified bands.
Nice. That's science.
Alien activity. And you have massive amounts of star formation. This black hole must be pretty active.
Yeah, but this is not any figure of AGN activity. We have to get the equivalent width, and if the equivalent width is small enough, then it is AGN. Otherwise, it is star formation rate indicator. So if the AGN is strong enough, it will destroy or like build up the continuum over here and destroy this line basically, and also the grains, how much it evaporates. So, yeah.
Do you have 1D imaging or spectroscopy for any of these studies?
No, this is the first spectroscopy in this region. Like the previous one I showed you, that's the IRAC image that we had. And this is first restaurant optical IR ever for this.
For all of these, we've hunted for AGN as best as we can, and we've never seen any strong AGN indicator ever. Yeah. I mean, presumably there's one in there, it's just highly obscured.
Yeah. So that's that. So the problems that I was talking about, basically what the institute is calling cosmic ray showers or cosmic showers. You can see these type of, so this is the channel that I'm interested in. There are 4 channels. This is a long detector. So this particular thing is where my power line will reside. And this is one particular aperture in the wavelength region of my interest. So this is how the data we get is aligned in 2D plane, and the cube is built after this. So in this plane, you can see there's some blobs over here, and that's cosmic ray showers. That's what they're training. There was updates last week trying to get better reductions from that. So the second part that we is over here, this is after high pass filtering this particular image and getting this, and that's the bottom panel spectra that you saw. So we are trying to get better reductions from that type of data.
So these are, so what is the scale of a pixel on here? These are, so like when I see one of these blobs, how big is it physically in the detector? Like micron?
This is physical detector.
Yeah, but
In the tube,
About that.
But like how big?
About an inch. About an inch.
Okay.
Maybe 2 inches.
like the whole detector.
And this is a tiny bit of
This is
that.
tiny bit.
Okay.
This is 1,000 by 1,000.
So these are like electrons playing pinball around in there,
Yeah.
producing a big cloud. Okay.
And this is only the third observation in the slow readout mode for this particular instrument. So there haven't been that many calibrations for maybe MRS slow readout mode. The recommended one is fast. So that's why if you are integrating for a longer period of time, you build up these type of things. So they're still trying to understand that. And like we are helping them understand what's going on, and they're helping us back. So speaking of AGN, this is the fresh data last week. I if I did this seminar last Friday, I wouldn't have this. So this is SPT-041A, near spec IFU data. This is integrated over the whole ring that you saw earlier. You can see H alpha, nitrogen lines, oxygen 6300, some sulfur lines popping up over here. So you can do a pseudo VPT analysis using these lines, and at least eyeballing this falls in the starburst category without AGN, so not AGN. If we do clumps, maybe we will find that, but that's still a work in progress. You might think like this is fairly easy to do, but it's not. It's like a niche. Like I think low redshift guys might be spoiled by this type of spectrum. So this is nothing that you get this in half an hour on CACOS.
So that's actually like the 1D spectra from everything.
Yeah, all the ring, complete.
Yeah. So yeah, like I don't know, integrated.
So integrated over this type of string. And oops, sorry, my bad.
I'm assuming that that's kind of calibrated.
No, so that's why we are waiting. We are expecting calibrations in a week or two. That will do the flux calibration much better. Right now, it can be off by lots of factors. It was definitely off during the first release. It's getting better. And I think in 1 or 2 weeks, they'll have a better reduction. And
That's pretty amazing.
yeah. So this is just integrated in this part for the last, I think this is what I've been looking at for a while last week. So I'm stepping through channels in DS9, starting over there and ending over here. You can see the companion popping up, then it clumps, on the clumps, and then it goes down over here, and then N plus pops up, and then goes down here. And that's the foreground lens. You had a condense meeting in August. That's the part of the whole collaboration. And questions, you get more data tomorrow.
Thank you. We have time for a couple of questions for Kedar.
Maybe it's a little early to say, but for the star formation rates from Passion Alpha and from the climbing stuff.
I haven't done that yet. Yeah, that's something. Yeah, I've been mostly doing the reduction. Any question?
To what extent can you like reconstruct the spatial, kind of like where those star forming clumps are?
We could do that. We have done that with Alma data, and David is here, is supposed to work on it. And also another grad student at Florida is working at it. So yeah, they're right now, I think, working on the imaging data. So it's easier to do it in imaging. And eventually with the IFU data, they'll be able to reconstruct the stuff on the clubs where they're coming from.
Okay, if there are no more questions, thanks, Kedar. Really interesting.
What conference is that?